Aloha, Rich Halverson here. This is ITS 388AL, and this is the first video of the semester. And so I'd like to just go over the syllabus and review the textbook and chapter one. So let me share my screen. Okay, AL, this one. Assembly Language Programming. In this course, we're going to learn about how microprocessors are programmed at the most basic level. It's not quite the ones and zeros level, but although it does, we still use mnemonics or code words, but they translate directly into the ones and zeros. And so we'll not only learn about a typical instruction repertoire or list of instructions or commands but we'll also learn how the ones and zeros actually manipulate the data paths inside the microprocessor and back and forth from the memory and so on. So this is an online asynchronous class. This is the textbook that we'll be using. I'll go over that in a moment. Cost $89. It's a Zybook, so all of the exercises and labs are in the textbook. And there is going to be a programming assignment at the end. So this is actually a simulation-based course covering microprocessor register level architectures, and this course is based off of the MIPS processor. And you can do a Google search on MIPS, and you can see where it's used and so on. And it's a good processor for teaching because it's nice and general, and it's not complicated with a bunch of other stuff. So that's the textbook. You can get to that when you click textbook, and we'll take a look at that in a moment. If you want to send an email to me or any of your classmates, you can go ahead and do that here. By the way, if you do want to send an email to your classmates and you want to exclude me, I'm not in here. Oh, yes, of course. I am in here because this is my student account. So if you'll see me in here as a student, you'll see my Gmail account. So if you want to, if you don't want me to see what you're, so whatever, I just point that out to you. This is the grade book, and I've already loaded up all these. And there are going to be some of these where you're going to write a simulator, a processor simulator, in any language you choose. In the resources, I've included the textbook from the last time I taught this class. And the last time I taught this class, we actually covered the Intel 86 microprocessor and its register set and all that. And it's a lot more complicated, and it deserved more than one course. But this semester we've sort of backed away from the complexity of this processor, and so we should actually, I think it's a much better course. But anyway, so you can take a look at that if you want to. It's kind of interesting. And you'll see like the register set and the list of all the instructions. One reason why the Intel processors are so complicated is because all throughout the life of the Intel processors that started out with a 4004 back in 1971, they've always tried to make the instruction set somewhat backward compatible. So you would be able to upgrade your processor and your old code would still work with the minimal or perhaps no amount of translation. And that just made it have to be more complex and so on. Anyway, Dropbox, in case you want to have me to take a look at your code, and maybe in the last assignments we'll do that. You may want me to take a look at your code. So if you go down to the the calendar here, I just, it's like, 2 weeks, 2 weeks per chapter. And then, and there's the participation and challenge and lab activities inside books, and then there's this programming assignment at the end. So let's take a look at the textbook. And we start out just talking about the numbering system, the number system that microprocessors use. And of course, they use a binary system. There's just ones and zeros. And then we have to convert from binary to decimal, which is what we're used to as humans. And so that's a lot what this talks about. And then how binary numbers are used to represent other things like letters and so on, and characters. And then how the sets of ones and zeros are used to represent integers or floating point numbers, and then how we do arithmetic, and then representing arrays and records or structures, which are kind of like arrays, but they're different types of primitive types inside of a record, and there's an array of records perhaps. And then how graphics are represented in memory, and image and video and audio. And then kilobytes, megabytes, and so on. Explains that here. So let's start by and then in chapter 2 we start to get into this what the processor looks like and how it connects to memory, and how instructions are fetched out of the program memory and executed in the processor, and so on. We'll see that there. All right, so let's start here and get through some of these. Let's take a look. Let's take a look at activity. So there's challenge activities in the first 5 sections of the. Oops, no, this is chapters. There's challenge activities in the first 7 sections of the first 8 sections of the first chapter, and then these are just participation, and there's no labs. In fact, let's see, do I assign any labs? That's right, I assign the labs separately. I don't think. Oh, it's not until next week, which we'll get to the first lab. So that means this lecture shouldn't take very long. Huh? All right, so you've probably read through all this already. I can see that a lot of you finished the participation activities. Here we're just talking about ones and zeros. A bit is a cell or a bit in memory, which can store either a 1 or a 0. And when you string 8 of them together, it's a byte, and so on. So a 1 or a 0 is called a bit. So you would say bit right here, bit. And you can check that, and it says correct. Okay, great. Binary digit. 8 bits are called a byte, and this one has 1, 2, 3, 4, 5, 6 bits. What's 6 bits? Is that a quarter? When you use 8 bits or 7 bits all together, and all the different combinations of 7 bits, there are 128 different combinations. When you have 7 bits, each bit can have a 1 or a 0, and those are mapped into characters, and they decided on this way back in the 1960s, and it's called the ASCII character set, American Standard Code for Information Exchange, and we've been using the ASCII character set ever since. And this is what it is. Space is decimal 32, which happens to be this is what it is in binary, and you see that they map up to 128 7. This would be the highest one, and the lowest one is down below 32 are um, different control characters like tab and character turn and so on. All right, so so go through this. What is a 7-bit code for lowercase a? Well, you can look here and find the lowercase a. It's right here. Okay, this is the uppercase a. So the uppercase a, this is the bit code. But for the lowercase a, this is the bit code. So we can just take this and copy this. Well, it's 1100001. So we can put 1100001 and see that that's the answer. What's the 7-bit code for a blank space? Well, that's 32 or decimal 32. That would be 0, 1, 0, 0, 0, 0. I think. Oh, it's got to be one more. One more here. So this is oh no, I bet it's okay, I'm guessing. Oh, I'm right. Okay. It's actually this one right here. Space. And what 2-letter word does the sequence of bits here represent in ASCII? Pay attention to upper lowercase. Okay, so this one is 1001000, and that would be 1001000. That's an H. 1001000 is H, a capital H. Capital H. And then 1101 or 1101001, which would be 1101001 is this one. 1101001, which is a lowercase I. Cute. Oops. I had my caps lock on. There we go. All right. So anyway, suppose an email message has 500 characters. How many bits would the computer use to store an email using ASCII code having 7 bits per character? Well, I guess it would just be 500 times 7, which would be 3,500. Methinks. Yes. Okay, let's do some challenges. Convert the this character. Let's just start it up and see. Convert the character to a 7-bit ASCII code. Okay, so it's S. We're supposed to convert S to a 7-bit ASCII. I assume that's a lowercase s. So what's a lowercase s? Is this 11110011. 111000. Did I say that right? 1110011. Okay. Okay, 1110011. Okay, what's next? Convert the character to a 7-bit ASCII code. The same thing. Okay, this is an example. Okay, 7. The capital. A 7 is this 0 0 1 1 0 1 1 1 0 1 1 0 1 1. All right, what's next? Convert the ASCII code into a character. Oh, okay. What is 1000101? 1000101. 1000101. Capital E. Capital E. Wow, what do you know? All right, I'll leave this last one for you to do. Okay, and so when you see text on the screen, even if it's a number, really what it is a string of characters like this, you see. See, this is SEAT colon space 9A. So this is SEAT colon space 9A. And see, these are the same kinds of things that we were translating back and forth up here in this challenge activity. So that's how that works. Characters, how many characters in the text displayed on the screen on the left side of the animation? How many characters? How many characters are in this animation? Let's see, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. 8. Is that right? Yes. How many memory locations are used to store the text? Let me see, maybe 8? Oh, look at that. The first letter in the text is S. What bits are stored in the first memory location? S, well, okay, it's 101011. 101011. 101011. Oops, forgot one of the zeros. 001. Okay. What is the minimum number of bits that each memory location must be able to store in the above example? What's the minimum number of bits that each memory location must be able to store? I guess 7, huh? How many total bits are needed? Okay, so you see that, right? Because it only goes, we're always only using 7 bits, even though these memory locations actually have 8 bits. All right, how many bits are needed to store? How many total bits are needed to store the text shown? You mean total bits here? 8 times 7 is 56. I guess that's what that means. Let's see. Yep, I guess so. All right. So published in 1991, uses more bits and then can represent more items, and such as symbols and so on. And so, of course, it uses more bits. It uses twice the number of bits. Instead of 8 bits, it's 16 bits. And so that's what Unicode is. And so it's similar, like capital A is still, is this is hexadecimal, isn't it? Yes, this is hexadecimal. See, it goes up to F and then, but anyway, so that's 41. It's still the same as up here. A is 41. Well, 40, this is 4, and this is 1. Gee, they're confusing you. They're confusing us already. Okay, anyway, so this is displayed in hexadecimal. We will learn about that, I guess, in in section 4. Okay, I better pick it up here. Okay, convert the character Convert the character to 4-digit hexadecimal. Have we talked about hexadecimal already? Oh, where are we? Convert the character into a 4-digit hexadecimal code point. Okay, so A equals U plus that. Capital A must be oh, I would say 0041 just as a guess. U plus 0041 just as a guess. Yeah, what do you know? A is that. Lowercase a is that. Capital, I mean, a 1 is 0031. Anyway, so you can go ahead with that. Convert that. I'm doing 4. I was able to skip to 4. I don't think you can skip to 4, but I am just to show you can do 3 yourself. Convert the hexadecimal Unicode code to a character. What's 0023 is a hashtag, I guess. Yeah, okay. Okay, so now let's talk about binary numbers. And so when you string the bits together, like when you string eight of them together, you have a byte, and so that's 8 binary digits, and in 8 binary digits, you can that's 256 combinations of ones and zeros that you can fit into eight bits. And so that's what we're going to learn here. So counting up in decimal and binary. So here when we count up to 10, and then we start over again, and 0 through 9, and then we start over again. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. In binary, we only have 2, so 0, 1, and then we have to, add a place, and we add a 1 here, and that's 0 and 1, and then we have to go farther than that and add. This is what comes after 1. It's 2, 0, 1, and then this is 3. So anyway, that's how you count it in binary, but still, this is 6. This is a value 6. And this is a value 6. This represents 6. This represents 10. This represents the value 10. Here's 10 stars. See, so this is like unary almost. This is unary. This is decimal, and this is binary. So make sure you click through that. Type the next higher 3-digit binary number, 001. How about this one? This is 0. Oh, this is 010. So we're just counting. All right, we'll just count it. Here we add 1, and so it ends up being 100 because we add 1 and makes it 0, carry the 1, 0, carry the 1. So this is just being able to count in binary. All right. Can you count from 0, 0, 0, 0 to 1, 1, 1, 1 in 20 seconds? Yeah. Oh, am I supposed to write 0, 0, 0? Oh, then what do I do? Oh. So, converting from binary to decimal. All right, so so what you do is you, as they say, multiply it out. And it's pretty easy because for each place, you know, you basically add them up. And so what do we do here? Oh, okay, so let's do reset. Okay, so like 2 is 1 0 is 2. You know, 1 0 1 0 is 10. 1 0 1 1 is 11, and so on. 1 1 1 0 is 14, and so on. And so what you do is, let's say it's this, you take 0 and 2 to the 0 power is 1, 2 to the 1 power is 2, 2 to the 2 power is 4, 2 to the 3 power is 8, 2 to the fourth power is 6, is 16. So for example, let's say you have this, you have 1 times 16 is 16, plus 1 times 8 is 8, so 16 plus 8 is 24, nothing here. And then you have 1 times 2 is 2, so 24 plus 2 is 26, and then nothing here, so that's why we get to 26. Convert from binary to decimal, use the fewest decimal digits possible. Yeah, recall the weights. So this is 1, this is 2, this is 7, this is 9, and this is 15. Oops, 15. Convert the 4-bit answer. I mean, type a 4-bit answer. Oh, 4-bit answer. Okay, so this is 4 bits, 0, 0, 1, 1. This is 0, 1, 0, 0. This is 0, oops, 0, 1, 0, 1. And this is, see, 12 is 1, 1, 0, 0 is 12. So this must be 13. Yeah, okay. All right, so fiddle with this. Bits required to represent a number. A computer has a limited amount of storage available to represent numbers as bits. So the number of bits available to store a number defines the range of numbers that can be represented. So of course, if only 2 bits are available, you can only store a 0, 1, a 2, and a 3. Anyway, determine the minimum number of bits required to represent each decimal number. Well, just 1. Here would be 3. This is 105 is 101. 15 is 1111, so 4. And 16 is 100. Oh, it's 5. So it's 1. So it's 10000 16. Okay, so adding binary numbers, it's see here, it's just like adding decimal numbers, except for you only have zeros and ones. So if you add 1 plus 1, that equals 2. Well, there's no 2. 2 is 1 0, so it's 0 carry the 1. So here we take 1 plus 0 is 1, 1, and then we have 1 plus 1 is 1 0, so that's a 0 carry the 1. And then 1 plus 1 plus 1 is 3. That's really 1, 1. So that's 1 carry the 1. And then 1 plus 0 is 1. So you can see that this is the result. And 1, 1, 1 is, of course, is 7. And 1, 1, 0 is 6. And so 6 plus 7 is 13. And so this is 13. All right. So we can do this binary addition one. Now we know how long this is. Going. Oh, it's been going 32 minutes. Okay. So binary addition. Oh, okay. So start. All right. Am I supposed to add this? Okay, 1. And this is 1, and this is 0, and this is 1. This is 0, 1, 1, 0. This is 0, 1, 1, 0. All right. Ignore the fifth bit. 0, carry the 1. 0, carry the 1. Carry the 1. 1, 0. And this one is 1. This is 1 plus 1 is 0, carry the 1. 1 plus 1 plus 1 is 3, which is 1, carry the 1. And then 1 plus 1 is 2, 0. Right. Okay. Whoops. 2, 3, 3, 1. And this is 7 plus 7 is 14. Oh. The last one is 12 plus 15 is 12 plus 15 is 20, let's see, 27, 16. Well, it's going to end up being 12 plus, it's going to end up being like it's 11. It's going to be 11, which is 1, 0, 1, 1. That's what the final answer is. Let's see. 1, 1, 0, carry the 1 is a 1. Okay, yes. Oh, I forgot to carry the 1, didn't I? All right, this is 11 plus 15 is going to be 10. 1, 0, 1, 0. That's going to be the result. 1 plus 1 is 0, carry the 1. 1 plus 1 plus 1 is 1, carry the 1. 1 plus 0 plus 1 is 0, carry the 1. 1 plus 1 plus 1 is 1. All right. Wow. Okay, the carry bit may cause the result to have 5 bits. Yes, so you can just do the same thing that we did up there. This is 2. Carry the 1 is, I'm doing this backward. Okay. It's going to be, okay, it's 5 plus 1. Okay, 5 plus 7 is 12. So that's 1, 1, 0, 0. Yes. Okay, anyway, okay, here we explain overflow. And when things get carried into the next bit, you know, when things get carried into the fifth bit, then that's an overflow. So, you have to be able to detect that, and it generally causes an error way down in the processor. So it's always if there's a carryover. So here, this is 7 plus 7 is 14. There's not going to be an overflow. Here we have 8 plus 7 is 15. There should be no overflow with 15. But 8 plus 8 is 16. So then we have an overflow. So, anyway. All right. Now, how do we represent negative numbers? Well, we have this way of representing it called 2's complement. And and the way 2's complement works is it's actually where if you take like some number and then you take the minus of that number, like let's say you take the number 7, and then you add to that the 2's complement of 7, which is minus 7, you end up with 0. So so just as 7 is 7 notches away from 0 in the positive side, minus 7 is 7 notches away from 0 in the negative side. And if you add a minus 7 and a plus 7, whatever the representations are in binary, it'd be 0, 1, 1, 1, and then minus, and then I guess what we're going to see now is how we figure out what the 2's complement number is. Okay, so we don't do sign magnitude, we do complement. All right, so 2's complement representation. Let's go through this so we can see that. In base 10, 5 minus 3. Five minus 3 is 2. So 5 plus. Okay. What the third? Minus 3. If in base 10, say 10 is the biggest number you can have. 5 minus 3 equals 2, right? 5 plus 7 equals 12, which is 2 with a 1 over here. But if you ignore the 1 over here, you just end up with a 2. And so we see that 5, if we're only dealing with 1 digit, we're not doing 2 digits, we're just doing 1, 5 minus 3 is the same as 5 plus 7. And because the reason is because 7 is the 10's complement of minus 3. I guess that's the way to say it. 7 plus 3 equals 10. 7 is the complement of 3, be 10's complement of 3. Thus, 5 plus 7 is too much, so the carry can be ignored. Okay, so what's next? In base 2, it's easy. You just invert the bits and add 1. See, so this is 3. Yeah, so this is 3, 0, 0, 1, 1. And so to make the minus 3, first you invert the bits, you get this, then you add 1 to it, and you get 1, 1, 0, 1. Okay, so minus 3 is 1, 1, 0, 1. Whereas plus 3 is 0, 0, 1, 1. Okay. So this you can tell if a number is really represents a negative number when we're doing 2's complement, because the highest order bit is going to be a 1. So it's called the sign bit. All right, it's called 2's complement representation. In base 10, what is the complement of 33? Well, it's actually 100 minus 33, which is 67, I think, right? Yeah, because 33 minus plus 67 is, okay, anyway. In base 2, what is the complement of 0, 0, 1, 1? Well, we start out by making it 1, 1, 0, 1. That's just complement. That's just inverting all the bits, and then we add 1 to it, and adding 1 to 1, 1, 0, 1 makes it 1, 1, 1, 0. So if we check that, we see that it's right. First we invert the bits and then we add 1 to it. What is minus 2 in 4-bit 2's? What is minus 2 in 4-bit 2's complement representation? Well, 2 would be 0, 0, 1, 0. And if we complement the bits, we get 1, 1, 0, 1, 1, 1, 0, 1. And then we add 1 to it, and we end up with 1, 1, 1, 0. Wow. What do you know? All right. What is -7 in 4-bit 2's complement representation? Well, +7 is 0, 1, 1, 1. And if we complement that, if we invert all the bits, we get 1, 0, 0, 0, 1 with 3 zeros, 1, 0, 0, 0. And if we add 1 to that, we get this. So I guess it's that. All right. Assuming 4-bit 2's complement representation, is this positive or negative? Well, it's negative because it's got the 1. So that's right, negative, right? I guess I write negative. Yeah. Assuming 2's complement representation, what base 10 number does 1, 1, 1, 1 represent? Well, if it's normally it'd be 15, but it's minus. Well, okay, so if this is a 1, then this is a negative number. So to be able to find out what the negative of that is, which would be the positive, it would be 0, 0, 0, 0, but we add 1 to it, so it's that. So I guess I would say -1. -1. Yes, it is. Assuming 2's complement representation, what base 10 number does that represent? Well, this is 2's complement. Since this is a 1 there, that means it's a negative number. So what is it? What is the positive version of 1001? It'd be 0110 plus 1 is 0111, and that's 7. And so I guess it's -7. -7. Oh, yes, it is. Anyway, so you can do the rest of those. Subtracting by adding. Okay, so the way you subtract a number is the way you do subtraction is you there's the subtrahend and the minuend, and then you subtract the minuend from the subtrahend. And so what you do is you take the minuend and you take the 2's complement of it, and then you add it. So really, subtraction is like adding, because you just take the second, you take the one that you're subtracting, and you take the 2's complement of it, and then you add it. Okay, so you take, or if you're doing it in base 10, you can take the 10's complement and then add it, and then ignore the upper digit. Okay, so assuming 4-bit 2's complement representation, 6 plus 2 is equal to 6 plus, I don't know, 2 is 0, 0, 1, 0. Yeah. 6 plus -2 is what's the 2's complement of -2 is it'd be 1, 1, 0, 1 plus 1 is 1, 1, 1, 0. Okay. 3 plus -4 is 3. Is this -4? -4 is 0, 0, 1, 0 plus 1 is Is this -4 4 minus 4 would be 0, 1, 0, 0. Well, anyway, I'm just supposed to say what this is. This is 1, 1, 1, 1, which is minus 1. So am I supposed to put 1, 1, 1, 1? Yeah. Okay. Anyway, 2 minus 3 is 2 plus minus 3 is minus 3 is 0, 0, 1, 1. That's plus 3. So minus 3 is 1, 1, 0, 0 plus 1 is that. And minus 3 plus 2 is oh, I'm supposed to put what minus 3 is right here, I guess. And minus 3 is, well, didn't I just do that one here? I'm going to put 1, 1, 0, 1 again. Yeah. Okay, so the largest positive 4-bit 2's complement number is this, and so it's a 7. The smallest one is this, which is 8. And so it can go from minus 8 to 7. Adding 2 positives or adding 2 negatives may yield a value that can't be represented. And so if that happens, there's overflow. And how do you tell if there's overflow? It's if the 2 overflow occurs if the numbers being added have the same sign bit, but the some sign bit differs. If they have different sign bits, then they can't overflow. So as seen above, overflow occurs if the numbers being added have the same sign bit, but the sum's sign bit is the opposite, or it differs. In other words, overflow occurs if 2 positives sum to a negative number, or if 2 negatives sum to a positive number. But if you add a positive and a negative, you won't overflow. You'll never overflow, so you don't have to worry about that case. All right, so that's overflow. Let's see, it's one. This has gone for 50 minutes already, and we are finishing up 1.3. All right, well, I think I'm gonna finish this, and I'm gonna end this video, and I will start a new video a little later. So here, let's do this one. Decimal complement of 9 is 1, because 1 plus 9 equals 10, or 10 minus 9 is 1. The binary complement of 0, 0, 1, 1 is, it would be 1, 1, 0, 0 plus 1. So it would be 1, 1, 0, 0 plus 1. So just that. And the binary complement of 1, 1, 0, 0 is 0, 0, 1, 1 plus 1 is going to be 1, 0, 0. And the binary operator, what's the answer? Let's see. 1 plus 0 is 1. And then 0 plus 1 is 1. And then 1 plus 1 is 0, carry the 1. And then 1 plus 0 plus 1 is 0, carry the 1. that right? One plus one is 0, carry the 1. Okay, yes, I think that's right. Okay, so what's the answer here? It would be well, you know, this is like minus 1. 1, 1, 1, 1 is like minus 1. So I can take 1, 1, 0, 1, 1, 1, 0, 1, and subtract 1 from it. Because it's like adding this is like subtracting 1. Adding 1, 1, 1, 1 is like subtracting is like subtracting 1. So if I have 1, 1, 0, 0, and I subtract 1 from it, I just get 1, 1, 0, 0. Let's see if I'm right. Yes. So what's the last one here? Well, that's just 1, 0, 0, 1. 1, 0, 0. It's 5 plus 4. 5 plus 4 is 9. Okay, that's looks good. And so I've done sections. I've done sections 1.1 to 1.3. I'll come back and do the remaining sections, and I'll try to do them more quickly. Okay, so thanks for watching.